Hi everyone, welcome back. Very good evening to you all. Can someone just please confirm if I am audible and visible? All right, so everything seems good to me. So how was your contest? So before starting the discussion, I wanted you guys to rate the entire contest on a scale of 10. And in case if you are rating less than 3, then please justify your reasons as it would help us to improve the upcoming problem set. So kindly rate on the scale of 10. 2 out of 4. And the first three problems were very easy. And the last problem was bit tricky, but can be solved using a monotonic stack. Don't worry, we'll explain all the four solutions. 10 makes sense. Yeah, question 4 was great. All right, so I guess we are good to go. So I will be taking this session off camera to avoid any kind of glitches. So let me just quickly share my screen and write a +1 if my screen is visible to you and I am audible equally. All right, so from my side, everything seems good to me. And yeah, so starting with the very first problem, array game. So you are playing an array game in which you are given two arrays ARR and BRR, each of size n, and each array is a permutation of n positive integer. Please note this point: all the integers in the given array are distinct. And in one operation, you can perform either of the following two steps. First, rotate the array anti-clockwise, basically the left shift operation, and then the second operation, remove the first element of the array if they are same. And our task is to report the minimum number of operations required to make both the arrays empty, right? So let's just quickly see the solution here. So the very first thing, all the elements are distinct, right? So basically every mapping of every element is fixed. This one can only be mapped with this one, right? When both the elements are same and at the front of ARR and BRR, then only we can remove both the elements, right? And the first operation was mentioned here, that we are allowed to perform rotate the array in anti-clockwise direction, right? So basically if we had a A1, A2, A3, A4, A5, then using one operation we can simply convert it to A2, A3, A4, A5, and then A1, right? So basically anti-clockwise rotation. So this is the first operation, and if the first element of ARR and BRR are same, then we can simply remove it. And we need to report the minimum operations that we require, minimum number of operations that we require to make both the arrays empty, right? So the basic observation is that mapping of every element from array ARR to array BRR is fixed, right? This one can only be removed when both the elements are at the front of the array, right? So this fixes the operation, and this problem can be solved just by implementing or basically the simulating the operations. What are the operations given to you? Simply simulate it. If the first element of the array are same, then remove them, right? Otherwise, rotate the array in anti-clockwise direction. So which one is the ideal data structure? So let's just first see what are the operations we required. So A1, A2, A3, A4, and A5. Then next array, instead of ARR and BRR, I am writing A and B, B1, B2, B3, B4, and B5. So I will simply check if A1 and B1 are same, then we can simply remove it, right? And if that is not the same, if they are not same, then what I can do, I can simply use one operation and make this A1 last element. So we'll perform the anti-clockwise operation. And then again, I will check if B1 and A2 are same, then simply remove it. Otherwise, we'll move this A2 at the end. We do not have any other option, right? So you just have to simulate the operation. So which data structure is an ideal data structure for this one? Is it Q, right? I will use a queue data structure. And why queue? Because we are removing the element from the front, right? And adding the element at the end. So the ideal data structure for this problem is queue. So let me just quickly explain it using this operation, this example. So the very first thing, I will insert all the elements of ARR to this queue. So we got 1, 2, and 3, right? And then we'll iterate over the elements of BRR. So starting from the very first element, so the first thing that I will check whether the front element of the queue is equal to the BRR element. And if they are equal, then we'll simply remove it. So we'll initialize our answer with 0. And now I will check whether the current index element, which is 2, and q dot front are same or not, and they are not same. So what I will do, I will remove the element from the front of the queue and insert at the back, right? So basically means we are performing the first operation of type 1, this one. Rotate the array anti-clockwise, right? And then again I will check the same thing. So whether the front of the queue element at the front of the queue is equal to the current index of BRR, and they are same. So what I will do, I will remove this 2 from the queue and will move to the next index. So we are at 1 now. Again I will check whether q dot front is same as BRR of index, and they are not same. So again I will perform the operation and rotate in anti-clockwise direction. So how many operations so far I have performed? So first of all, I have moved this one at the end. So one operation for that. Then yeah, removing 2. Then second operation. Then I am going to move this 3 at the end. So we'll move this 3 at the end. Right? And this cost one operation. So we'll increment our answer by 1. So now it is equal to 3. And then what I can see here, again I will check the same thing, whether the q dot front and BRR of index are same or not. And this time they are same. So what I will do, I will simply remove them. So we'll remove this one and increment the index. Now we are at the last element. And since removing the operations also cost one operation, so we'll increment the answer. Answer is equal to 4. Now again q dot front, which is equal to 3, is equal to BRR of index. So again we'll remove it, right? And again increment the answer by 1. So the minimum number of operation that is required is 5. And let me just quickly check the expected output. It is also 5 for the first example. So and here is the implementation. So queue, then inserting all the elements of ARR to this queue, then answer total operation, basically initializing it with 0, then index variable with 0, which refer to array BRR, then running a while loop while queue is not empty. Then we'll first check if the queue dot front is equal to BRR of index, then an happy case will simply remove it and increment the index. Otherwise, what I will do, I will remove it and insert it at the end, and both the operation cost us one move, right? So we'll increment the total operation. And after this, we return this total number of operations. So let me try to submit this. Accepted, right? So now can anyone tell me what is the time complexity? Anyone? What is the time complexity of this solution? What is the time complexity of this solution? Linear or quadratic? So actually both has the same meaning. You can either rotate ARR or you can either rotate BRR. Linear. No, it's not a linear. It's a quadratic. Here the time BRR is sorted in descending order. 3, 2, 1. So in this case, you will require 3 operation to remove this one, right? 3 operation for the first element ARR of 1, or let me just quickly simulate it. So initially we insert 1, 2, 3 in this queue, right? So what I can see here, for this 3, how many operations that I need to perform. So the very first thing, the first operation, I will move this 1 at the end. So one operation for this, 2, 3 and 1. Then I will move this 2 at the end. So 3, 1 and 2, right? And now 3 and 3 are same, so we can remove it, right? So one operation for that. So after removing 3 and 3, the remaining in this will be the structure of the queue, right? So how many operations we have performed? 1, 2, 2 rotations and 1 operation of the second type. Basically remove the element if they are same. So we require 3 operation for this, 2 operation for this, right? Here in this case, you will first apply a rotation and then remove this 2, then one operation for this, right? So the time complexity in the worst case is the sum of first and natural number, and the sum of first and natural number is n into n plus 1 and divided by 2, right? Or I can say, since it is a big O notation, so I can say the time complexity is n square. So is it clear to everyone? Okay, just allow me 1 minute. If there is some network issue. Is now it is visible to you? Right, a plus 1. right? So the time complexity in the worst case is n square. And why it is n square? So consider this case when one array is sorted in ascending order and another array is sorted in descending order. So in this case, for removing the first element of BRR, you require three operation, basically n operation, then n minus 1, then n minus 2, and so on till n. So for example, let me just quickly simulate this for the first example. So yeah, I'm explaining it again. So in the worst case, one array is sorted in ascending order, while other array is sorted in descending order, right? So how many operations do we require to remove this three? So we first insert this one to 3 in the queue, right? So what I can see, 1 is not equal to 3. So I will remove this one and move at the end of the queue. Basically, I am performing the operation of the first type, and or more formally, I can say rotating the array in anti-clockwise direction. So this will be the new configuration of queue 231. Then again 2 is not equal to 3, so I will again move this 2 at the end of the queue, performing one more operation. So this will be the new configuration of queue, and this time what I can see, 3 is equal to 3, so I will remove this 3, right? And we'll move to the next index. And after removing this 3, the final structure of the queue is 1 and 2. Inside our queue, we have 1 and 2. And how many operations do we perform to remove the first element of ARR? It is 3, right? 3 operation. Then how many operation do we need to perform to remove this 2? So basically we have 1, 2. So in one operation, what I will do, I will move this 2. So 1 not equal to 2. So I will remove this 2 from the front and add it at the add at the end. So 2 and 1, right? And this time they are same. Q dot front and BRR of index, they are same. So we'll remove it. So how many operation in total we require? We require two operation. One operation moving the 2, basically anti-clockwise rotation, and the second operation for removing it. So in total we require two operation, and after this removing this 2, we are only left with 1, and it is equal to BRR of index. So I will simply remove it, right? So we require one operation for it. So in the worst case, the time complexity is the sum of first n natural number n into n plus 1, and the formula for sum of n natural number is n into n plus 1 by 2, right? Which is, and since we are writing a big O notation, so I can say it is n square. So write a plus 1 if it is clear to you. Right, so I guess this was enough for this problem. Let's just quickly discuss the next problem, which was a maximum distance. So given an array of length n denoted as x, basically array x of length n, where each element represent the coordinate of n police stations. And let's consider the Geek resistance marked at coordinate A, and the distance from Geek's home to the ith police station is expressed as absolute value of A minus x of I, right? And our task is to select two indices, distinct indices I and j, such that the maximum absolute difference is maximum, right? So basically we are given an array, x, right? Which are representing the coordinate of n police stations, right? So array x of length n, and our task is to select two indices I and j such that the score is maximized. And this is the score for I and j, the absolute difference of x minus a and x of j minus a, right? And this a, which is the initial location of the geek, will be given to you. So is the problem statement clear to everyone? Write a +1 if the problem statement is clear to you. So the very first thing, I will sort the coordinates in ascending order, right? And once I have sorted this coordinate in ascending order, then now let's break down this problem into multiple cases. So what are the possible cases we can have? So we have a coordinate from x0, then x1, and then x2, and so on till x of n minus 1. And I have assumed that the coordinates are sorted in ascending order, right? So what are the possible cases we can have? So the very first thing, we want to maximize this score, right? And this is an absolute difference, right? So we want to select the coordinate as far as possible to the given coordinate a, right? So what can we are the first case? So the very first case, when a is between x0 and x of n minus 1. So let's say somewhere at here. So if a is somewhere at here, and if you want to maximize the score, then which coordinate you will select? Definitely x of 0 and x of n minus 1. So this will be our first case. Then what are the other possible cases? If a is not between x0 and x of n minus 1, instead it is before x of 0, then which two coordinate you will select? If a is at here, definitely you will select this one, right? X of n minus 2 as the first coordinate, basically x of I, and x of j. You will select this one. And the last case, when a is after the coordinate x of n minus 1, basically somewhere at here. So which coordinate you will select? This one, right? X of 0 and x of 1. So from these three cases, what I can see, potentially only these four coordinates are important. Our answer is lying within these four coordinates, and we'll select two of them. And since it is a constant number of possibilities, so we can explore all the possibilities for these four coordinates. So is it clear to everyone? Write a +1 if it is clear to you. I will simply extract these four coordinates and simply apply a brute force. Write a +1 if the solution is clear to you. So let me just quickly show you the implementation. So first of all, I am sorting the coordinate in ascending order, then extracting the first two coordinate x0 and x1, then last two coordinate x of n minus 2 and x of n minus 1, right? And there might be a case when the number of coordinates is less than 4. So in that case, I will update this vector with uh, with the given vector, right? If the number of coordinates given to us is less than 4. And after this, we are simply applying a brute force and select the maximum two indices which are giving the maximum score, and then returning the answer. So this is the complete solution, and I hope it is clear to everyone. Is there any doubt? Yes, no, anything? Okay, don't worry, Speedy. It would take not more than 10 minutes. The third problem was very easy and will take not more than 5 minutes to explain it. So then the third problem, geek and buildings. So you are given an array heights of n elements whose ith element denote the height of the ith building, and Geeks likes to jump from one building to another, and he only jump to the next taller building. And please note this point, Geek cannot skip any building, and he is restricted to jump to the next taller building, or basically I can say next greater element, logic here, and stop when he reaches the tallest building. Basically, he stop at the building for which the next greater element is not there, and the energy required for his journey is XOR of all the heights of the building on which geeks jump until he stop. And geek can start his journey from any building, and we need to report the maximum energy required before he start. So let me just quickly explain you the, and I guess the example is very much clear to you. A very great explanation is given to you, basically all the possible cases. So let me just quickly explain you the solution. So geek and building. So this is a very standard problem of our dynamic programming. So let's just quickly define a dynamic programming. So dp of I, let's say dp of I is the maximum XOR value if geek start his journey from building I, right? And but wait, this is not the correct basically this is not the 100% appropriate definition. And why I'm saying 100% appropriate, because see, you are not allowed to skip any element, right? You are restricted to move to the next greater element. So in this case, saying maximum is not true, because we do not have different possibilities. We have only one possibilities: from I move to the next greater element. So if I write the transitions here, so dp of I is equal to height of I XOR dp of next greater element of I, basically index of next greater element of height of I. So next greater element of I, right? And we all know how to find this thing. This is a very standard problem of a monotonic stack. And for every element, you can find the next greater element index in just a linear time using a monotonic stack. And I'm not going to explain you this. You can yeah, watch some editorial regarding this monotonic stack to find the next greater element. And this is the transitions, and if you draw the recursive tree, then you will find that the problem are having overlapping subproblems, so we can memorize it using a dp. So that's why I'm using a dp array. So this is the transitions, and in this way we can solve this problem. And what will be our answer? So our answer is equal to maximum value of dp of I. So answer is equal to maximum value of dp of I. So I from 0 to n minus 1, because it was mentioned that geek can start from any building. So that's why maximum value of dp of I. So this is the complete explanation for this problem. Now let me just quickly show you the implementation. And here is the logic to find the next data element for every index. And the logic of monotonic stack has been used. We store the elements in strictly decreasing order, and when we got some element, we remove all the elements which are lesser than this. Or let me explain it to you. A very quick overview of this monotonic stack to find the next greater element. So to find the next greater element, what I will do, I will store the elements inside the stack in decreasing order. Don't get confused, not in strictly decreasing order. So in this way, A1, then A2, A3, and A4, right? And if we got some element A5, which is greater than A4 and A3, then what I will do, I will remove A3, and the next greater element of A3 is A5, right? Then next greater element of A4 is also A5. So we'll remove it from this stack, and the new configuration, the new structure of this stack will be this: A1, A2, and A5, right? And if we again got some element A6, so we'll initialize the next greater element of all the elements in the stack which are having value lesser than this as A6. So this is the logic for a monotonic stack to find the next greater element. And once you get this thing, then simply declare a dp vector or array and initializing every value with 0, then initializing answer with 0, and then iterating from right to left. And why from right to left? Because see, to fill the value of dp of I, we need dp of next greater element of I, right? And we know this is on the right side, so that's why I'm moving from right to left. So before filling the value of dp of I, we know we have already computed this value. So that's why this time we move from right to left. And if the next greater element is not present, that is the value of next greater element of I is equal to -1, then we do not have anything. So the dp of I is equal to height of I. Otherwise, dp of I is equal to temp, which is equal to height of height of I XOR the dp of next greater element index. And answer would be equal to maximum of dp of I. And we'll simply return this answer. So is it clear to everyone? Write a +1. So submit it. And what is the time complexity? Anyone? Is it linear or quadratic or something? Write a quick +1 if it is clear to you so that I can quickly explain you the last solution. And the time complexity and the space complexity both are linear. So the last problem, which is a minimum pass. So in a school assembly, your class students are standing in a random order, and now you need to rearrange them in a non-decreasing order of their height. And in one operation, you can remove all the students who have their height less than the student in front of them. Or more formally, heights are given as an array, and the student removed in one operation, the student removed in a operation will be the ith student, where h of height of the ith student is lesser than height of I minus 1. And more formally, you are given an array height of size n, and our task is to return the minimum number of moves after which the height the heights become non-decreasing, right? So please note this point. It is not mentioned that strictly non-decreasing, but only mentioned here that non-decreasing. So let me just quickly discuss the solution here. So some of you might wondering that this is same as the previous problem. Find the next greater element for every element, and then the number of elements between the next greater element would be our answer. But wait, it is not true for all the cases. So let me explain you with an example. And one suggestion from my side, while solving these type of problem, the best way to analyze the pattern or draw the observation is to use this histogram kind of a pattern. Always draw a bar and then try to find the pattern. So some of you might wondering that find the next greater element, and the answer would be equal to number of element between the next greater element. So for example, this 10, the next greater element is 11, right? The next greater or equal element is 11. So in this case, you might think that answer would be equal to how many elements are there? 3 and 3. Answer is equal to 6. but it is not true, right? Answer not equal to the number of elements in between. So then what is our answer? So in the first operation, this bar will get removed, right? Because it has height lesser than the height of the student on the left side. 8 is less than 10. Then again 7 is less than 8. So this will also get removed in the first operation. This will also get removed in the first operation. And it has height greater than the height of the student on its left. So it will not get removed. But when these three get removed in the first operation, then in the second operation on the left of this we have 10, right? Which is less than, which is greater than 4. So this get removed in the second operation. This get removed in the second operation. This one get removed in the third operation. Then this one get removed in the fourth operation, right? So our answer for this case is equal to 4. Now let's just quickly expand this problem, and we'll add one more student at the front. Then how our answer will change? So if you are adding an student whose height is lesser than whose height is lesser than this one, then it would totally fine, right? And happy case. But what if it has height greater than this student? Then will our answer will change? No, your answer will remain as it is, and this building will get removed. So in the first operation, this one will get removed, then this one will get removed, then this one in the first operation, and this one again in the first operation. Then in the second operation, this one, third operation, and the fourth operation, right? So in this case, your answer will not change. If you are adding and building on the left side, which is having height greater, then your answer will remain as it is, right? So are you getting a kind of pattern? Then that is between any two bar x and y such that y is greater than or equal to x, the number of operations that we required is the number of segments, number of strictly decreasing segment. Please try to pay more attention here. Here we have our first strictly decreasing segment from 10 to 3, then second strictly decreasing segment, then fourth, then third strictly decreasing segment, and then the fourth strictly decreasing segment, right? So let's call this entire bigger segment as D. So D of maybe 0 or maybe 1. Then we can have multiple segments, multiple such segment, then D of 2, then another segment D of 3, and so on so far. Then what will be our answer? So is this thing clear to everyone? D1, D2, and D3. Write a +1 if it is clear to you. Write a +1 if it is clear to you. Right? So we can have multiple such segment D1, D2, and D3. Now let me just quickly generalize this. So for any two bar x and y, for any two bar x and y such that x is less than or equal to y. So the number of operation, what is the minimum number of operations we require to remove all the bar, right? Basically, I'm assuming that for this x, y is the first greater or equal element. So how many minimum operations do we require to remove all the bar between x and y? So we know it is equal to the number of strictly decreasing segment. So let's say to relax this smaller segment, it require D1 operations, then second segment require D2 operation, then third segment require D3 operation. Then what this are bigger segment from X to Y required. So the number of operations that we required is equal to, so let's say D is equal to maximum of D1, D2 and D3. And if now let me just quickly break down into multiple cases. So if D, this maximum D1 is equal to maximum among these three smaller segment. So if D is equal to D1, then our answer, or let's say answer is equal to basically the minimum operation required to relax this segment from X to Y. And when I say relax the segment, basically means I will fix it, and X and Y will now in increasing order. And or more formally, I can say I will remove all the bar between X and Y. So let's say C is equal to 0 and C is storing the current answer. So in this case, if D is equal to D1, then the number of operations that we required is D1, right? Plus 2. So first I will remove all the bar of this segment, right? And we know D1 is equal to the maximum among D1, D2 and D3. So this one will get relaxed, right? Because D1 is taking maximum time, and this one also get relaxed before D1. So then one operation for this and one operation for this. So that's why plus 2. And what if D is equal to D2? So if D is equal to D2, then C would be equal to D2 plus 1. And why I'm saying 1? So see, this time D2 is taking the maximum time, right? D2 is taking the maximum time. So before relaxing D2, D1 will get relaxed, right? So that means we have removed all the bar of segment D1, right? And now we are removing the bar of segment D2, right? And it takes D2 operation and then plus 1 for D3. And what if D is equal to D3? So in this case, we know D3 segment D3 is taking the maximum time, right? So before relaxing this segment D3, all the segment D1, D2 will get relaxed. So in this case, our answer would be equal to simply D3, right? Because we know we have removed all the segments D1 and D2, all the bar of D1 and D2, right? So this would be our answer. So now if I generalize this thing and write a formula for this or logic as per my implementation, then I can say we'll initialize our C with 0, the current number of operations, and then we'll iterate over the smaller segment. Let's say from 1 to the number of smaller segments. And our answer is equal to C is equal to max of C plus 1, right? Comma D of I. And both has the same meaning. You can check from here as well. And then inside the stack, what I will do, I will push this thing. So I will use a stack, monotonic stack, and inside this stack, what I will do, I will push the number of operation to relax building X and Y. So I will push two things. The first one, height of the last building, or basically not a building but a student. Height of the last student X and comma the minimum number of operations, which is equal to C, right? Basically what I'm doing, I'm compressing the bars here, or I am compressing the students to optimize the solution. And yeah, this is the complete solution. Let me show you the implementation here. So using a monotonic stack pair, which is of pair of int comma int, first I am storing the height. First I will store the height and then the number of operations that we require. And definitely we move from right to left, right? As we are assuming the new building on the left side. Then if stack is empty, then simply add this height, and the operation required is 0. Otherwise, initializing C with 0 and D with 0, right? And then removing all the students which are having height lesser than the height of the ith student. We'll remove all such students, and D is equal to st.top.second, and then we'll remove the student from the stack, and updating C, basically the number of operation to relax the current segment is equal to maximum of C plus 1 comma D, and answer would be equal to maximum of such C. and then we'll add this thing inside the stack. And after this, we'll simply return our answer, because we can have multiple such segments. We can have multiple such segments. We can have another segment here, then another segment here. So that's why answer is equal to maximum of such C. So this is the complete solution, and the time complexity and the space complexity both are linear. So clear to everyone? Write a +1 if it is clear to you. Is there any doubt? Or we can wrap this session. So recommending you to rewatch the recording of this session, and then try to analyze the pattern. And I admit that this problem is the hardest problem of this contest. So you can also prefer a recording and try to think that what I have discussed here. First, I have explained this case, then adding one building with height greater than the last building, and then analyzing the pattern, that answer would equal to remain, answer will remain as it is. We can have multiple such segment, let's say D1, D1, D2, and D3, right? And then, yeah, this observation. And we are using a monotonic stack. So make sure that if you are familiar with the monotonic stack, then with go this problem, otherwise you can skip it. Right, so thank you so much guys for joining the session. Hope you have learned something new, and also your feedbacks are really important for me, so do share your feedback to improve the upcoming sessions. And yes, have a great day and wish you a very happy new year.